And welcome back. This should be the last video for the entire semester. So, hope it's been a fun ride, or at least an educational one. It always means the same thing. Well, I'm not even that idealistic, but this one, we're looking at systems of inequalities. There's some relation to systems of equations, certainly in their definition, but a system of inequalities is just a set of inequalities you're considering simultaneously. So the first thing, before we get to systems, we're going to look at how to graph an inequality, specifically an inequality in more than one variable, because we've been graphing inequalities in one variable on the number line for a long time. But to graph an inequality, you graph the associated equation and then you start shading. So for example, if I had negative 3x plus 7y is greater than 21. Actually, that's exercise 13, and I will do that in a second. But for right now, well, I actually forgot to write something in there. I'll fix that in just a second. I want to do 11 first. Negative 2x plus y is less than or equal to 4. So we are going to graph the associated equation. So if this were equals, this would be a line, and I just solve for y. So y is less than or equal to 2x plus 4. And if you sketch that, this is not going to be a great sketch. I can already tell. It's hard to be precise with these with my graphics tablet. I'm just not that strong of an artist to keep my hand that steady. Let's see, 1, 2, 3, 4. So that's enough to get the general idea. Okay, this thing goes up 2 and over 1. So up 2 over 1, up 2 over 1. Basically looks like this. Okay, that's the boundary of the solution, though. The key is everything below, because y is less than, will actually satisfy the inequality. So, for example, if I plug 0, 0 in, 0, 0, the point 0, 0 would satisfy the inequality because I'd have 0 is less than or equal to 4. Every point below the line would satisfy that inequality, so you need to indicate they're all solutions, and you do that by shading. If you got a pencil, obviously you can use the side of it and do that, but I just generally am, well, I don't know, I could shade pretty nicely with this. I didn't think I would be able to. Yeah, if you got a pen, I mean, I would just do lines like I was doing before. That's generally what I have to do on board in class because I'm just using dry erase markers. Now, an important thing though is about the boundary itself. If it's less than or equal, everything on the boundary actually works. So like this point right here, that would be 0, 4. 4 is less than or equal to 0 plus 4. Yes, it is less than or equal. But over here, if it were strictly less than, anything on the boundary would not work. So you have to indicate the difference between those. So for greater than, less than, you want your boundary to be a dashed line to indicate there are no actual solutions on the boundary. Whereas if you're doing greater than or equal, less than or equal, you want a solid line to indicate everything on the boundary, as in here, is a solution. I forgot to put that in here. So this one, 7y greater than 21 plus 3x. And then y would be greater than 7. It is greater than, sign that, greater than. Y is greater than 7 plus 3/7 x. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So I have a y-intercept at 7. This thing would go down 3 and over. Put myself a little guide here. 7. And I screwed up that a bit because this should be a dashed line. So I will fix it. Okay, and then y is greater than that line, so everything above it should be a solution. Exercise 17, where I have x squared plus y greater than or equal 3. Well, let's see. Y is greater than or equal 3 negative x squared plus 3. Well, if you graph that, negative x squared plus 3. I'm just going to make a very simple graph here, but it's a parabola. And it's downward facing. And it would be solid because it's greater than or equal. But this is everything above it. I actually got a little bit inside there, sorry. So everything up here will be part of the solution. And something like 19, you would have to recognize what this graph is. X squared plus y squared equal 100. That, if you remember from back in chapter 1, is a circle with a radius of 10. I'm sorry, it's not equal 100, it's greater than or equal 100. Well, this is equal to radius, x squared plus y squared, because, you know, in general it's x, the standard equation of circles x minus a squared plus y minus k squared equals the radius squared. So I like to think about this as this means the radius squared must be greater than or equal 100. So that means everything outside the circle. If it were less than, it would be everything inside the circle. Let's see, only other thing I would have to say for just a basic inequality would be something like exercise 7. If you have x less than 2, well, that would, x equals 2 would be a vertical line at 2. Now I don't have y in this case, but I can still shade because if x is less than something, it's going to be to the left. So yeah, etc. in WebAssign, there's a little paint can you can use. It's like the fill can in any paint program you can use for shading. Alright, now let's talk about systems of inequalities. So if you have a system of inequalities, that would be several of these inequalities you're considering at the same time. You want to draw all boundaries and then shade the area that satisfies all inequalities. So I do suggest you use arrows as a help for that, but it's kind of up to you. If a problem asks you to find vertices, each vertex is just an intersection of two boundaries, so you take those two inequalities and solve that system of associated equations. Because a common point would be where they're equal. That's what we're doing in systems of equations, is finding common points. So that's what you would do. Okie dokie. Let's solve some systems. So we're going to do exercise 6. We're going to graph/solve the system of inequalities. And we're going to find all vertices. It does say to determine also the solution set is bounded. Alright, so if I want to solve this, I need to graph these. So negative y less than negative 3x plus 21. Divide out the negative, y is greater than 3x minus 21. And then 3y greater than negative 2x minus 12. So y will be greater than negative 2/3 x minus 4. Okay, so for this, well, my horizontals are better anyway. Oh. One, two, 3, 4, 5, 6, 7, 8, 9. That's negative 5. 10, 11, 12, 13, 14, 15. Three, 4, 5, 6, 7, 8, 9, 10. Okay, so at negative 4, it goes down to over 3. 2. And these should both be dashed. The other one, let's see, I can't really use the, I don't want to go down to negative 21. So let's start at, say, 5. At 5, it would be negative 6. And then it goes up by 3 and over 1. Also dashed. Now, what I meant by the arrows. Well, you know it's supposed to be greater than 3x minus 21, so you make little arrows to indicate that in the different areas. And then it also has to be greater than negative 2/3 x minus 4, so it also has to be greater than this line. Well, you can see then pretty easily where it has to be. Can't be down here because it's not above either. Can't be here because it's not above this one. Can't be here because it's not above this one. Only can be up here. That's the area. Vertices. Determine whether the solution set is bounded. It's not bounded. It goes infinitely off this way. That's what they mean by whether it's bounded or not. If I had like a third side going this way that cut it off, it would be bounded. But it's not. So unbounded solution. And then the vertice, well, it'd just be where they're equal. So if this was y equals and this was y equals, let's just set them equal. 3x minus 21. You might be able to read it off. It looks like it might be at, what is that, 5 negative 7 maybe? Let's actually just check that. If it were 5, it'd be 10 minus 7 minus 21 would be negative 11. No, that doesn't look right. Okay, so it's probably not that. Let's see, 3x minus 21 equal negative 2/3 x minus 4. So I get all the x terms on one side. Might as well clear fractions as well. So 3 times everything, 9x minus 63 equal negative 2x minus 12. Move the 2x over, 11x equal, let's see, 63. Add 63, subtract 12, you get 51. So x would be 51 over 11. That's close to 5. And then y would be 3 times 51 over 11 minus 21. So, this is a job for the calculator. I could work it by hand, but I've got the calculator to do the arithmetic for me, so I might as well. I was right. It's very close to where I expected it to be. Negative 78 over 11. So, let's see if that satisfies both. 2. Oh, hit the wrong one. 2 times 51 over 11. Plus 3 times negative 78 over 11. Oh, I screwed up. Oh, bother. Yeah, I made a mistake here. Add minus 12 when it should be plus 12. Well, that's a problem. Plus 4. Well, that's going to make a difference. So, I screw up the other one? No, I didn't. So, as well just erase that graph completely. There's nothing that's correct about it. So, now I got negative 2/3 x plus 4. So, goes down, 1, 2, 3, 4, 6, 7, 8, 9, 3, 4, 5, 6, 7, 8, 9, 10. So let's see here. Oh, has a y-intercept at 4, goes down 2 over 3, down 2 over 3, and again I forgot it has to be dashed. This side doesn't really matter that much anyway, but let's see, I should make sure I got the right one. There you go. Boom, boom, boom. Okay, and then the other one. Let's see, 6 negative, what was it? Negative 3x minus 1, yeah, 3x minus 1. So at 6 it would be 18 minus 1 would be negative 3. And at 9, that's 7, it would be 0. Honestly, that's good enough for what I need here. So my arrows would still be pointing up from both. So it'd still be up here. Alright, so that's the solution area. The vertex then, okay, that would have been plus 4, plus 12, I screwed up, didn't I? It was the 21 that was the problem. No. No, that was right. That was right. Well, that's going to be 12 plus 63 would be 75. So it'd be 75 over 11. Okay. And then y would be 3 times 75 over 11 minus 21. Well, let's see what that is. Just going to go to my previous answer and change that. Second enter does that and do 75 over 11 instead of 55 over 11. And math fraction to convert. Negative 84 over 11. Okay then. That can't be right. Yeah, it looks like I... Oh, it's not right. Second answer, second answer, second answer. Three times 75 over 11 minus 21. That's what I want. Okay, that's reasonable. Math, fraction, fraction. Negative 6 elevenths. Okay, so I've got 75 over 11 and 6 elevenths, so negative 6 elevenths. So let's check those. 2 times 75 over 11 minus 3 times 6 over 11. Okay. 3 times 75 over 11 minus negative 6 over 11. 21. Okay, that's the vertex. So the only vertex is at 75 over 11, negative 6 elevenths. I'll leave this in just to illustrate some of the difficulty you get into with doing the solving. I just made a bunch of errors, so I had to find them. Okay, let's do exercise 50. So here's exercise 50. I have x squared minus y is greater than or equal to 0. I have x plus y is less than 6. And I have x minus y is greater than 6. So, y is greater than or equal, no, negative y is greater than or equal to negative x squared, so y is less than or equal to x squared. So, 0, 0, 1, 1, 2, 4, 3, 6, 7, 8, 9, 3, 9, 1, 2, 2, 4, 3. This is a solid. Should be a solid boundary. Okay, and then we have y is less than 6 minus x. So 1, 2, 3, 4, 5, 6. So it's downward facing, so it goes down 1 over 1. Down 1 over 1. Well, that's convenient. Oh, that one. Is dashed. One up 1 over 1. Up 1 over 1. It actually would go through that point. And then the other one would be y is less than 6 plus x. So that would look like that. Okay, so we're below, above, yeah. No, above, below. Thought I was just going to be in this thing, but No, I'm in this thing. Okay, so this is the area. If it's below everything, then vertices. Well, the only really vertices I care about are these, because they're the only places my boundaries touch around my area. By the way, this is unbounded, and I think I can read both of those off. Those are both at 2, 4, and negative 2, 4. And check those fairly easily. I know it's on that thing. 2, 4, negative 2, 4. Let's see, 2, 4 would be 6. Yep. Then negative 2, 4 would work in the other one. I screwed up. Well, I screwed up again. 6 minus x would be wrong, so this line is wrong. So it should be x minus 6, which should be 4, 5, 6. Should be going up 1 over 1 there. So it should just be in here. In that case, another boundary you consider here. Okay, so that one doesn't exist. Just this one. So if you're above that, everything in here, still unbounded in 2 directions. In this case, the only vertex would be this one, and I guess that one. No, wait a minute. 6 minus x. Yeah, 6 minus x would be correct. So this one would still exist, but this one wouldn't. That one would get me right, but the other one, 6 minus x, yeah, this one is wrong. There's no one with positive over there. So this one is wrong. So the different vertices are here at 2, 4, with 2, 4, 6, yeah. That would work just fine. And here, which would be the intersection of the 2 lines, that'd be easy enough to take. You get x plus y equal 6 and x minus y equals 6. So you get 2x equal 12 and x equals 6. So y would be 0. Yeah, that'd be 6, 0. 6, 0 and 2, 4. Just verify 6, 0 works. 6, 0, 6, 0. Yeah, it works fine for both. So these are the 2 vertices. It is unbounded, and we're good. Alright, despite my problems with keeping the problem straight, not making any errors. This is the section. So, and that is the completion of all the material. So I would take a look at the final, and if you need any more help, I may make some supplementary videos if necessary. I will send out emails once I've finished grading the final. Alright, talk to you later.